Similarly, one more type, involutory matrix. Involutory means if A is a square matrix of order n by n such that A square equal to I, where I is also n by. The square of the matrix is unity matrix of same order. A is a square matrix of order n by n such that the square of that matrix, A square, is the unity matrix of n by n. Then A is called involutory matrix. Involutory matrix. If square of the matrix is A itself idempotent, and A power n equal to 0 and n being the least positive integer in such a way, then it is A is nilpotent of index n. And A is a square matrix such that A square equal to I, then it is involutory matrix. You have to observe the difference between these three. So, involutory means the square of any square matrix is identity matrix of same order. Then it is said to be involutory. Now, take one problem on this definition. If A equal to 4 minus 1 minus 4, 3 0 minus 4, 3 minus 1 minus 3, then show that A square equal to I 3 by 3. That means here you have to show that the given square matrix A is involutory matrix. So, for that, let us consider A square. A square is A into A, that is 4 minus 1 minus 4, 3 0 minus 4, 3 minus 1 minus 3 multiplied with 4 minus 4 minus 1 minus 4, 3 0 minus 4, 3 minus 1 minus 3. Now, taking the product, row to column product, 4 into 4 16, minus 1 into 3 minus 3, minus 4 into 3 minus 12. First row second column product, minus 4 0 minus 4 minus 1 product plus 4. Similarly, first row third column product, minus 16 plus 4 plus 12. Second row first column product, 12 0 minus 12. Second row second column product, minus 3 0 plus 4. Second row third column product, 3 into minus 4, minus 12, 0 into 4, 0 and plus 12. Next one, third row first column product, 12 minus 3 minus 9. Third row second column product, minus 3 0 and this is plus 3. Third row third column product, minus 12 and plus 4 plus 9. This is 16 minus 15, that gives us 1. Minus 4 plus 4, 0. This is 16 minus 16, again 0. 12 minus 12, 0. Minus 3 plus 4, 1. this is 0. Minus 9 minus 3 minus 12 plus 12, that is 0. Minus 3 plus 3, 0. Minus 12 plus 4 plus 9, 13 minus 12, 1. Clearly it is a unit matrix of order 3 by 3. Hence A is an involutory matrix. Once A square equal to A, that is idempotent. If A power n is 0, where n is least positive integer, then A is said to be nilpotent of index n. In case of A square equal to I, then you can say that A is involutory matrix. You observe the difference between these three. Next problem. If A equal to 3 minus 4, 1 minus 1, then A power n equal to 1 plus 2n minus 4n, n 1 minus 2n for all positive integer n. Prove by mathematical induction, principle of mathematical induction. You have to prove, then otherwise you take here as prove that if A is 3 minus 4 and 1 minus 1, then prove that A power n is 1 plus 2n minus 4n n 1 minus 2n for all n that belongs to n by principle of mathematical induction. Now you have to apply mathematical induction to prove this integral power of A as 1 plus 2n minus 4n n 1 minus 2n. So first step, initial step, step 1. For n equal to 1, because n belongs to set of natural numbers, I am taking n equal to 1. For n equal to 1, in A power n, from A power n, A equal to 1 plus 2 into 1 minus 4 into 1, 1, 1 minus 2 into 1. I am taking n equal to 1 here, taking n equal to 1, we get in this matrix 3 minus 4 and 1 minus 1, which is A itself. So for n equal to 1, the statement is true. For n equal to 1, given A power n equal to 1 plus 2n minus 4n, n 1 minus 2n is true. N equal to 1, this is true. N 1 minus 2n is true. In case of n taking n equal to 1, that gives us A itself. So which is true. Already A is given as 3 minus 4, 1 minus 1. In principle of mathematical induction, assumption step. Let us assume that for n equal to k, the statement is, what is the statement? A power n is this. So A power k is 1 plus 2k minus 4k, k 1 minus 2k, k being a positive integer. Let us assume that a power k as 1 plus 2k minus 4k, k 1 minus 2k. Now step 3. We have to prove the statement is true for its next successive power. That means consider a power k plus 1. A power k plus 1 may be written as a power k into a by the integral powers. A power m into a power n is a power m plus n is followed in case of matrix product. So a power k into a gives us a power k plus 1. Here a power k is 1 plus 2k minus 4k, k 1 minus 2k, which is assumed as true. And a is, you can take a as 3 minus 4, 1 minus 1. Because the statement is true for n equal to 1, I am taking a as 3 minus 4, 1 minus 1. Now taking the multiplication here, row to column wise product, row to column product, 1 plus 2k into 3, 1 plus 2k into 3 plus 1 into minus 4k, of course. Similarly, 1 plus 2k into minus 4 plus minus 4k into minus 1. First row, first column product, first row, second column product. Similarly, second row, first column product. Second row, second column product. So on simplification, this is 3 plus 6k minus 4k. That gives us 3 plus 6k minus 4k gives us plus 2k. Here minus 4 minus 4 minus 8k plus 4k minus 4k minus 4 minus 8k plus 4k gives us minus 4. 3k minus 2k gives us k, so 1 plus k here. Minus 4k plus 2k gives us minus 2k minus 1, minus 1 minus 2. Now I will write this one. I will write this therefore. A power k plus 1 as 3 plus 2k may be written as 3 plus 2k may be written as 1 plus 2 into k plus 1, which gives us 2k plus 2 plus 1, 3 plus 2k. Now coming to this one, minus 4 into 1 plus otherwise k plus 1. This is 1 plus k itself. And this one is 1 minus 2 into k plus 1. 1 minus 2, 1 minus 2 gives us minus 1, minus 2k. 1 minus 1 minus 2k may be written as 1 minus 2 into k plus 1. And just we are getting in place of n k plus 1. So a power k plus 1, a power k plus 1, replacing n with k plus 1, we get 1 plus 2 into k plus 1, minus 4 into k plus 1, 1 plus k or k plus 1, 1 minus 2 into k plus 1. So which is true for n equal to k plus 1 also. And using this one, assuming this a power k is true, we can able to prove a power k plus 1 is also true in this case. So therefore, for n equal to k plus 1 also, the given statement is true. The given statement, what is the given statement? If A is this, A power n is this. Hence, the conclusion step 4 is by principle of mathematical induction, finite mathematical induction. For all n that belongs to n, A power n is the matrix, given matrix 1 plus 2n and minus 4n and n 1 minus 2n. So, you can apply principle of finite mathematical induction to prove such problems. Now, the concept of transpose of a matrix. Transpose of a matrix. Transpose of a matrix. If A is Aij of m by n matrix, then transpose of A that is A transpose or A dash is Aj of n by n matrix. That is A transpose equal to the matrix Aj of n by n. Once A is Aij of m by n, by interchanging the rows and columns, I am interchanging the rows and columns here. Once you interchange the rows to columns, you get the transpose of that matrix. The transpose of the matrix is denoted by A transpose. I read it as A transpose or A dash. A dash or A transpose stands for by interchanging the rows and two columns of the given matrix, the obtained matrix is transpose matrix. For example, A equal to X, Y, Z, A, B, C, that is A, B, C, 1, 2, 3. Then A transpose. Write the rows as columns here. Just you write the rows as columns. The first row X, Y, Z as column. The second row as second column. And third row as third column. This is A transpose. Simply interchanging the rows to columns. Interchanging rows to columns or columns to rows. You get the transpose of that matrix. So, once Aij of m by n is the given matrix, then its transpose is Aji of n by m, n by m. Similarly, one more example. Suppose A is 2, minus 3, 4, 5, 6, 7, 2 by 3 ordered matrix. Then its transpose. Then its transpose is, write the rows as columns here. The first column is 2, minus 3, 4. The second column is 5, 6, 7. The order of this matrix is 3 rows and 2 columns, 3 by 2. 3 by 2. So in such a way, once you are interchanging columns to rows or rows to columns, you get the transpose of the given matrix. Now coming to properties of the transpose. Properties of the transpose of a matrix. Properties of transpose. Transpose of matrix. Coming to properties of transpose of a matrix. The first one is A transpose, whole transpose is always equal to A. Where A is the given matrix, the transpose of transpose. A transpose and again transpose. A transpose means you are interchanging rows to columns. And then again rows to columns, we get the same matrix. A transpose is nothing but AJI. A transpose gives us again AIJ, the original matrix, elements of the original matrix. Hence, A transpose equal to A itself, transpose of transpose. Easy. The second property is A plus B. Once addition is possible between A and B, A plus B whole transpose, A, B are of same size, A, B are of same order, then addition is possible. Then A plus B whole transpose is nothing but A transpose plus B transpose. A transpose plus B transpose, where A comma B are of same order. The addition is possible. Once the addition is possible, then A plus B whole transpose is A transpose. You can write it as A transpose plus B transpose. Similarly, A minus B whole transpose is A transpose minus B transpose. Just addition, you can take subtraction also. Next, K A whole transpose, where K is being a scalar, K into A whole transpose is K into A transpose itself, where K be a scalar. And the fifth property is an important property. A B whole transpose. Both A and B are conformable to take the multiplication of A B whole transpose is B transpose A transpose. Just reverse the matrices and take the transpose. A B whole transpose is B transpose A transpose. Reversal law. It is called reversal law of transpose of the matrix. So, A B whole transpose is B transpose A transpose. Where A B are conformable to take the product. You can generalize that one. Suppose A, B, C and so on. Whole transpose. Once you consider A, B, C and so on, whole transpose may be written as C transpose, B transpose, A transpose. Next property. Once you consider the diagonal matrix, I will consider the 3 by 3 diagonal matrix. Suppose A1 0 0 0 A2 0 0 0 A3. The diagonal matrix, only it has principal diagonal elements, the remaining elements are zeros. Once A1, A2, A3 are principal diagonal elements of the diagonal matrix, and you consider the transpose of the diagonal matrix, then you get A1, 0, 0. I am writing the row as column. Similarly, second row as column, third row as column. We get the same matrix. That is diagonal of A1, A2, A3 whole transpose is diagonal matrix itself. The transpose of diagonal matrix is itself. So we can conclude that the transpose of I unit matrix is I itself. The transpose of unity matrix of n by n is n by n itself. The transpose of a scalar matrix is itself. So like that, any diagonal matrix, once you consider any diagonal matrix, the transpose of the diagonal matrix is itself. Once you consider an upper triangle matrix, its transpose becomes lower triangle matrix. Once you consider lower triangle matrix, its transpose becomes upper triangle matrix, like that. By interchanging rows and columns, we get the transpose of the matrix. Now, based on transpose of the matrix, some problem. If A be a square matrix, then show that first one, A plus A transpose is do one thing. I will give certain definitions and then we will go for problems. Now, symmetric matrix. Based on transpose property of the matrix, symmetric matrix is defined. If A is a square matrix such that A transpose equal to A, the transpose of A is A itself, then A is called symmetric matrix. That is, if A equal to Aij of n by n and A is symmetric, then Aij is equal to Aj for all I comma j. Once A is a square matrix and A transpose equal to A itself, once you interchanging the rows to columns, there is no change in the matrix, then it is called symmetric matrix. So once you interchanging, Aij becomes Aj, but once A transpose equal to A, these two are equal. So in such case, A is symmetric. Skew symmetric matrix. Similarly, skew symmetric. If A is a square matrix such that A transpose equal to minus A transpose equal to minus A, then A is called skew symmetric matrix. Skew symmetric matrix. That is, if A is Aij of n by n is skew symmetric, then Aij is as minus Ji for all A comma J. Aij equal to minus Aj for all I comma j. So, once the transpose of the matrix is minus A, square matrix is minus A itself, then we get the skew matrix. That the square matrix is called skew matrix. Once A transpose equal to A, it is symmetric matrix. For symmetric matrix, the example is, suppose I will take the symmetric matrix as A transpose is A itself. A transpose is A. So 1, 4, 5. 4 minus 3, 6. And 5, 6, 5. Once you consider A as like this, then A transpose. A transpose is changing rows to columns. 1, 4, 5. 4 minus 3, 6. 5, 6, 5. Once again we get A itself. 1, 4, 5. 4 minus 3, 6. 5, 6, 5. That is A itself. So, this is of square matrix which is symmetric. In symmetric matrix, you can observe that, of course, in 3 by 3 matrix, these two are equal, and these two are equal, and these two are equal. The principal diagonal elements never changes. Once you interchange the rows to columns, it changes to this place. It takes this place and it takes this place. So, once A transpose equal to A, these two must be equal. Similarly, these two must be equal. Similarly, these two must be equal. So, A1, 2 position becomes A2, 1. A1, 3 position takes A3, 1. Once you interchange. So, hence, these two elements are equal. These two elements are equal. These two elements are equal. By observing that one, you can say straight away the given matrix is transpose, the symmetric. The transpose of the matrix is A itself. Coming to skew symmetric matrix, I will take like this. A as 1 minus 4, 5, minus 5. 4 minus 3, 6. 5 minus 6 and 4. I will consider, so this is, this one is 0, 0, 0. Because Aij must be equal to minus Aji, then principal diagonal elements must be 0. So, once you consider A as 0 minus 4 minus 5, 4, 0, 6, 5 minus 6, 0, then here A transpose, I will consider that transpose. The transpose Once you write the rows to columns, 0, minus 4, minus 5, and 4, 0, 6, 5, minus 6, 0. Multiplying a with minus 1. Minus a is 0, 4, 5. 0, 4, 5. And here we get minus 4, minus 6. And here we get minus 5, plus 6. Minus 5 plus 6, 0. So, which is clearly minus. So, this is the example for skew symmetric, and this is the example for symmetry. You can observe that in skew symmetric matrix, these two elements are numerically equal and they are of opposite sign. These two are numerically equal. Numerically equal means they are differed in sign. Similarly, these two are numerically equal, they differed in sign. Similarly, these two are numerically equal, they differed in sign. And the principal diagonal elements always 0 for skew symmetric matrix. That is one very important point related to the skew symmetric matrix. So, note point, you take it as a note point. Note point. In skew symmetric matrix, the principal diagonal elements are always zeros. In skew symmetric matrix, the principal diagonal elements are always zeros. Here, the principal diagonal elements are always zeros. That is one important point related to skew symmetric. Otherwise, it cannot be skew symmetric. Once I equal to j, a11 equal to minus a11 here, I equal to 1, j equal to 1, a11 equal to minus a11. This is possible whenever 2a11 is 0, a11 is 0. Simply each and every element in the principal diagonal of the square matrix becomes 0 once the square matrix is skew symmetric. Now,